Hello everyone, I'm Jue Wang from Nanjing University. Today I'm here to talk about our work for detecting non-crashing functional bugs in Android apps via deep state differential analysis. My co-authors are Yan Yanjiang, Ting Su, Shaohua Li, Changxu, Jianlu, and Chen Dongsu. Our work is about detecting non-crashing functional bugs in Android apps. But first, let's talk about the movie first. In a World War II movie, Inglourious Basterds, directed by Quentin Tarantino, the character, who is a British spy pretending to be a German officer, was exposed by the Gestapo because of a careless action. When making a three-finger gesture, the spy did as on the left side, while the Gestapo observed that most people in the German make the gesture as the right side shows. He then established a belief that right side gesture is a common behavior, while the left side is an individual one, and thus identified the spy. Such an idea has long been used for automatically detecting non-crashing functional bugs in programs, introduced as the bug as deviant behaviors idea in 2001. The main idea is to infer programmer beliefs and cross-check for contradictions as signs of non-crashing functional bugs. The main advantage of this approach is that no prior or knowledge of truth is required, which is often hard to obtain. Now, for detecting non-crashing functional bugs in Android apps, we found that we face similar situations. We often also lack prior knowledge of truth, and the non-crashing functional bugs also often exhibit deviant behaviors. Let's look at a real bug example in Amaze, an Android app that manages files on the phone. In most situations, the GUI layout of Amaze looks like this, displaying a list of folders of files. When clicking one of the folders or zip files, Amaze will display its content correctly. However, if the user clicks an empty folder inside the zip file to view its empty content, Amaze incorrectly identifies the empty folder as an APK, i.e. an Android installation file, and calls the APK installer to install that folder. This is clearly a non-crashing functional bug. During an automated testing process, such a non-crashing functional bug can be occasionally triggered. But even so, it is very difficult to automatically identify it. This is because that automatic testing tools often lack detailed functional specifications or proper understanding to the app's logic. As a result, they have to rely on expensive manual validations to identify such non-crashing functional bugs. So how can we automatically detect such non-crashing functional bugs? As described earlier, we found that such bugs can also be identified as deviant behaviors. Specifically, we made two key observations. First, we observed that during an automated testing process, there can be many traces that end up with a similar GUI layout, and only a small portion of them end up with an erroneous state. This is because that developers would already notice and fix bugs on frequent program passes. Secondly, we observe that Android apps are often designed with the least spread principle, that performing the same actions on similar GUI layouts should trigger only a few limited outcomes. Based on our observations, we propose our approach named the deep state differential analysis and detect non-crashing functional bugs in Android apps as deviant behaviors. Given the app under test and its massive automatically generated traces of test inputs, our approach first groups these traces of our inputs so that each group ends up with similar GUI layouts. Next, our approach appends the same event to these inputs to manifest diverse app behaviors. Finally, our approach clusters these manifested behaviors and accordingly identifies majorities as beliefs, while the others as anomalies. Such an idea is non-trivial to apply on Android apps, and there are two major challenges. The first challenge comes from the distribution of the massive traces generated by automatic testing tools. For non-crashing functional bugs to be deviant behaviors, our first observation that only a small portion of the traces ends up with an erroneous state must hold. However, existing covariate-directed test input generators often provide inputs drawn from a highly skewed probability distribution, which can violate the observation. First, existing test input generators often have difficulties generating test inputs reaching deep states of the app. As a result, these deep states may lack sufficient traces for deriving strong beliefs on majority behaviors. Second, to maximize covered states or app code within limited testing time, automatic testing input generators tend to stick to a profitable trace for long-term exploration. If such a profitable trace is accidentally erroneous, they can no longer be identified as real and buggy. Therefore, our first challenge is that how to effectively obtain massive, balanced test inputs that provides all explored state FG GUIs, no matter shallow or deep, with sufficiently many traces of behavioral diversity. To tackle this challenge, our approach conducts a test input collaboration at the very beginning. Given the set of massive automatically obtained execution traces, our approach mans an GUI model of the app from traces by merging similar GUI layouts as GUI model states and adding transitions according to the input event between the GUI layouts in the traces. With GUI model, our approach calibrates the test inputs by approximating random walks on the model. For each walk, our approach selects the least balanced state as the target state. The least balanced state is the one with fewest trace reaching it. Then, starting from an initial state, our approach forces all our transitions from the same state, the same probability of being chosen, and accordingly selects the next step of the random walk. Such a random walk stops when the target state is reached. The path of the random walk accords to an additional test input. By repeating such a process, we can generate balanced, sufficient inputs for each GUI model state. As such, we mitigate the first challenge by a test input calibration. The second challenge comes from the third step, clustering manifested behaviors, which can be represented as corresponding GUI layout pairs. However, the GUI layouts often contain rich and redundant information, sometimes even non-deterministic information like dynamic web content. Consider the three layout pairs in the example. Most of these GUI layouts share many similarities, such as similar GUI structures and same titles. Meanwhile, they also have different but redundant details, such as different file paths. It's a challenge to find a deliberate abstraction that is simultaneously effective in distinguishing anomaly behaviors and resistant to noises. To mitigate this challenge, a GUI abstraction-based agglomerate hierarchical clustering is performed by our approach. Based on common abstraction criteria adopted by existing techniques, we design a set of abstraction rules that can be applied individually or combined. With each GUI layout pair in its own cluster with no abstraction, our approach selects one more abstraction rules and apply it to all layouts for further abstraction. After applying a new rule, our approach measures the similarities between clusters by comparing their fingerprints, which are obtained by calculating the differentials in each GUI layout's pairs using tree editing distance. Such a fingerprints enables us to focus on the instantaneous rate of changes and ignore the accumulated non-determinism over execution, just like the first-order differential of continuous functions. Clusters with identical fingerprints are then merged. After one round of GUI abstraction and cluster merging, our approach calculates these scores using each cluster size and identify any small clusters with a state score larger than 3 as anomalies. Such a hierarchical clustering process iterates until all abstraction rules are applied or any anomalies is found. As such, we mitigate this second challenge by such a clustering algorithm. We implemented our approach as a prototype tool Odin and used 17 real-world Android apps to evaluate its effectiveness. 11 of these apps are large or popular subjects evaluated in existing work. Furthermore, to conduct a full comparison with the state-of-the-art automatic Oracle Genie, we select the remaining 6 subjects that haven't been selected. We compare the bug-finding abilities with Genie on the numbers of bug reports, true positives, and detected distinct functional bugs. For each tool, we give them sufficient testing budgets. The results demonstrate that Odin and Genie are complementary to each other. Specifically, Odin reported 28 distinct non-crashing functional bugs, 5 of which were previously unknown. On the other hand, Genie reported 34 distinct functional bugs, 4 of which were previously unknown. 2 of these 4 previously unknown bugs reported by Genie were also reported by Odin. Additionally, we found that 17 bugs were reported by both tools, where Odin reported 11 bugs that are beyond Genie's scope. On the other hand, Odin achieved a 32.4% average report precision. The false positives mainly comes from imprecise GUI layout models, rare but normal behaviors, and unstable replay of the execution traces, which can be mitigated with more advanced orthogonal techniques. Note that Odin achieved a comparable precision with the state-of-the-art automatic Oracle Genie and have already largely reduced the required manual efforts for validation. Furthermore, to evaluate the effectiveness of our test input calibration and hierarchical clustering algorithm, we compared Odin with 2 of its variants on the 11 large or popular subjects. The first variant, OdinCalib, does not calibrate the massive automatically generated test inputs. We let it use the same inputs as Odin and directly goes to behavior manifestation and anomaly detection. The second variant, OdinSimple, adopts the simple clustering algorithms. It uses a fixed abstraction criteria for all GUI layouts, which is commonly adopted by existing techniques, and then merges clusters with identical fingerprints for only one round. The results show that Odin significantly outperformed its two variants. Specifically, on the 11 subjects, Odin reported 20 distinct non-crashing functional bugs with a 33.3 average precision, where Odin no Caliph missed 6 bugs due to the skewed distribution of the automatically generated test inputs. On the other hand, without the hierarchical clustering algorithm, Odin Simple only reported 8 non-crashing functional bugs with only 15.3% average precision. All of these 8 bugs were also reported by Odin. These results demonstrate that the effectiveness of our proposed collaboration and hierarchical clustering algorithms. In a short summary, we leverage the insight that a large number of traces obtained by executing automatically generated test inputs can reach similar GUI layouts, and only a small portion of them reach erroneous app states. It presents a generic automatic oracle named deep state differential analysis for detecting non-crashing functional bugs in Android apps by manifesting both normal and deviant behaviors and then clustering them to map beliefs and detect anomalies. We implemented our technique into an exploratory prototype Odin, and the evaluation results demonstrate that Odin can effectively detect non-crashing functional bugs in real-world Android apps. A considerable portion of them cannot be detected by existing techniques. Odin will be fully released soon, so please stay tuned. This finishes my presentation. Thank you for listening.